Hello everybody, nice to see you again and welcome back to Ask Math Anything. This happens to be one of our close to the end of the school year sessions. Actually, we've had a lot of fun talking about all of these different mathematics topics, and if you're new here, you're about to find out about some new mathematics topics that I don't know about either. The way that this works is that anyone can ask questions. And what I do is I try to find interesting questions to answer that I can explain in ways that make sense to people who are maybe thinking about algebra or geometry. Now, if you have been here before, you know that you're in for something that's going to be completely different. Actually, every single time that we do this session, just a second, someone said that there's no sound. Is that true? Seems like there's sound here. One double check. Is there no sound? This one seems to say there's sound. I'm just double checking what we have here. My mic seems to be sending sound. There is sound. Okay, so there is sound. That's good. I don't actually know exactly what's wrong with YouTube today, but in any case, we can deal with it, right? That's what we always do when we're trying to do and Ask Math Anything. So I actually already see there's a question by Grace Yan. Will these live streams continue during the summer? The current plan is yes. But again, the way that I work with my time is I go and decide what can I do with my time that is the most helpful. And as some of you know, I've been working on quite a few other projects at the same time. So to the degree that I'm able to keep running these live streams, I will. We'll see. Great. So if you've been here before, that's the kind of question you might ask, because I guess you're curious whether or not this will still be able to continue when there's actually no other school to attend. You see, what we like to do here is the opposite of school. Not because school is bad, but just because it's a different feeling. And what I want to do is I want to not be the one who is teaching you as much as learning from you what you want to learn. So what should we discuss? Let's see. What kind of questions do we have today? I see. Oh, okay, this sounds kind of interesting. Let's see if we can figure this out. It's a question from Angela Liu. And Angela Liu's question says that there are 30 students in a class. Lots of questions seem to start that way, classes of 30 students. And there's somebody named Carlos. Carlos made 13 errors. And all other students made fewer errors. They all made fewer errors. Show that at least 3 students made the same number of errors. So from all of this, what we're trying to find out is show that at least 3 students made the same number of errors. All right, these are kind of fun questions. This is related to something called the pigeonhole principle. The pigeonhole principle, what that happens to be is it happens to say that if you have 10 pigeons and if you have 9 holes that they go into, then they won't all fit. That's the idea. Carlos is smart. That's right. Carlos is the one who made the fewest errors. But the way that you think about these kinds of things is you say, well, if I want to prove something, let's prove by contradiction. Let's assume it's not true and see if we can get something that seems weird. That's the easiest way to think about these kinds of things. So to do this, what we'll do is assume, for the sake of contradiction, that actually there are no 2 students, so there are no 3 students who made the same number of errors. So what that means is for each number of errors from 12 on down, there are only 2 students. That for each number of errors from 0, 1, 2, up until 12, that there are only 2 students with each number of errors. At most 2. Uh-oh, so here's where we'll get in trouble, right? So if we happen to have that at most 2 people of each of these errors, how many people are there in the class? Can anyone answer this? What's the most number of people that could be in this class if I know that, of all of these numbers of errors, 0, 1, 2, up to 12, there are at most 2. Well, it's a trick question, actually. It's not 24 and it's not 26. I was asking how many students are there in this class. Not 24 and not 26. What's the most number of students that could be in this class? We're saying that for each of these numbers of errors, 0, 1, 2, up to 12, there are at most 2 students with that number of errors. So what's the most number of people there could be in this class? 25 is getting closer to the right answer. It's not 29 either. 27, Skylar, thank you very much. It's because for each of these 13 numbers here, you could have 2 people. And so that would give you 13 times 2 is 26 other people. And since there are 26 other people, that means that the maximum number of people in the class, including Carlos, we have to count Carlos too, is 27. So what this means is the maximum number of people in the class is at most 2 times 13 and then plus 1. That's Carlos. And that's equal to 27. And that's a contradiction. We were supposed to have 30 people in the class, and there are only at most 27. And that's what this pigeonhole principle is about. The pigeonhole principle sounds fancy, but really it's just an idea of arguing by contradiction. What the pigeonhole principle says is basically, if everything doesn't fit, then it doesn't fit. And that's exactly what we were doing here. We were saying just assume for the sake of contradiction that, we don't have 3 people. Then this is what we have, at most 2 of each. And then you just go and figure out how many people there could be, and that's it. Now, the pigeonhole principle is also, you can also argue about the pigeonhole principle another way. Let me show you another way to think of this. All right? So another way, which we think about in combinatorics, is to think about it this way. We say, all right, I have how many people? I have 30 students, and I'll think of that as 29 other students. So I'm going to rewrite on a new screen what I'm going to do now. Another approach, and this approach doesn't use proof by contradiction. So remember, the problem is 30 students. Carlos has big brain. Carlos makes 13 errors. Why are they keeping track of number of errors instead of problems correct? I don't know. They must be pessimists. But anyway, oh, that's supposed to say Carlos. It's hard to read. Let's do it again. Carlos makes 13 errors, and everyone else makes less. Hang on a second. Why are we saying that Carlos is the big brain? Carlos is the one who made the most errors. Oops. Maybe I had it backwards. But anyway, so if we have all of this, how many are the everyone else? The everyone else here is, the number of everyone else is 29 people. And what does makes less mean? The less here is how many different numbers of errors could they have made? Well, they could have made 0 errors, 1 error, 2 errors, up to 12 errors. Here, there are 13 numbers of errors. We can almost think of those as 13 buckets. I mean, you don't really want to throw people in buckets, but you could imagine that you did. Imagine that you had 13 buckets, and the buckets were just labeled 0, 1, 2, all the way to 12. I guess you also have Carlos here. Carlos is special. Carlos goes into Carlos's bucket. And then what you do is you just start throwing people into buckets based on how many errors they made. The person who's actually big brain goes here. Clearly that's the name. And then we've got like someone thrown into this bucket, and someone else is in this bucket, but someone else is thrown on top of them, right? You're just throwing all these people into buckets. So as all these people go into buckets, here's what I want to do. We're going to separate off Carlos with a wall. Carlos is just over here. Don't worry about Carlos. So now we've got all these people here who are thrown in buckets. And we happen to have how many buckets? 13 buckets. Now, here's something I want to ask. What's the average number of people that's in a bucket? Can anyone tell me that answer? I have here, among these 13 buckets. Ignore the bucket called 13. So among buckets 0, 1, up until 12, the average number of people in a bucket, well, that's equal to just 29 other people divided by 13 buckets, okay? Now, some people actually calculated this and got some decimal. But here's what I'm going to tell you. 29 over 13, it's 2 point something, right? Because 13 times 2 is 26. 13 times 3 is 39. So this is equal to 2 point something. Now, suppose I have all these buckets here. And suppose that the average number of people in a bucket is 2 point something. Could it be that all of the buckets have less than or equal to 2 people? Of course not. I mean, how could you have every bucket with less than or equal to 2 people and then somehow on average it's 2 point something? It doesn't work. So there's something you can always do. Whenever you know that the average occupancy of a bucket is something, then there always is a bucket which has at least this many, rounded up, many people inside it. So there's a bucket with at least, there's a way you can write this down. It's like a bracket, but not a complete bracket. That's hard to read. 2 point something, rounded up. This notation means you round it up to the next number. Rounded up, which is 3 people. And this notation here meant round up. Okay? And this is always true. Whenever I happen to have a bunch of things averaging, if all the things happen to be integers, because the number of people in each bucket is a whole number, then if I take the average of all of them, there's always a bucket which has at least one more. At least the round up, at least the ceiling function. Temp ID says the proper name for this is the ceiling function. That's right, because you're saying like somehow, if this is 2 point something, the ceiling is you go up to the like this, the ceiling, right? You go up to the next number, and that's 3. So this is another way of looking at how to do this problem. You could have just said, let's figure out how many other people there are, divide by how many buckets there are, and round up. And if you round up, you will know that there's definitely going to be a bucket, or a number of problems wrong, that had at least 3 people. All right, so that finishes this question. I see that somebody asked, what question are we talking about? Let's figure that out now. What question should we talk about? Let's see. Wow, this is an interesting one. Somebody has asked, can you give me advice on how to teach a 6-year-old? I'm trying to teach my little brother to get money. You're a very kind person trying to teach your little brother to get money. If you want to know how to teach a 6-year-old, here's what I would suggest. You actually really want to just develop their attention span. My opinion is that somehow if you wanted to go and teach people, especially at that age, the best thing you can do is to just let them try to think through things and try to understand. Just to give you an example, if they can do some basic addition, see if they can notice an interesting pattern, which is that if you add 2 and you keep adding 2, it's like always an even number. That's kind of neat. Or as soon as somebody understands how to do multiplication, you can try to do other kinds of neat patterns. I actually think that it's really interesting to go and learn that there are patterns in the world of numbers. And as you do this, you sort of are starting to form all of these circuits in your brain where you eventually look at anything and you find these patterns. That's what you should really be doing when you're 6. You don't just need to be memorizing a multiplication table. All right, more questions. 1, 2, 3, 3. Wonder if there's a pattern there. Oh, somebody asked, Vera Wang asked, how 1729 is interesting. That's a famous number. This number happens to be, I think we actually might have talked about it in one of these live streams, and if so, I'll just do it real quick. This happens to be very famous because it's the sum of 2 cubes in 2 different ways, right? This happens to be 10 cubed, that's 1000, plus 9 cubed, which is 729. But it also happens to be 12 cubed, which is 1728, plus 1 cubed. And it's the smallest number that can be written as the sum of 2 cubes in 2 different ways. More questions. I just saw that the battery is running low on one of the computers that I use in order to be able to see what you're writing. So I'm going to just go plug it in. 1 second, please. Hello again. At first when I saw that, so one of the computers gave me an alert saying battery is low, and so that needed to be charged or else we would not be able to see your comments. All right, more questions, more questions. Wow, so many questions. Just a second, I'm going to roll over to here. Oh, somebody has just told me that what I was finding is I was finding yesterday's questions. That's what was going on. So don't worry, we're going to make sure we talk about today's questions too. Oh, this looks interesting. Picklebothead has a question. You guys have the best usernames, by the way. So Picklebothead is asking, simplify a minus 1 times a plus 1 times a plus 2 minus a minus 2 times a plus 1. Okay, it looks like all we have to do is multiply everything out. You think I'm going to do that? By now you've probably figured out that I'm extremely lazy. If I ever have to do something by multiplying out, my immediate reaction is, can I find something else that I can do? And whenever I see stuff like this, I say, can we collect like terms? Exactly, we can factor that, I guess. Let's factor out the a plus 1. That should at least make our life a little bit easier. This is a plus 1 times a minus 1 times a plus 2 minus a minus 2. Okay, now the question is, can I do this? Well, I guess I could try to multiply it out and see what happens. If I multiply that out, then I get a plus 1 times, it's a squared minus 3a minus 2. Did I even do that right? No, I did it wrong. It looks fishy. A squared plus a minus 2. That's better. So a squared plus a minus 2, because that's a squared. This is a plus 2a minus an a is plus a single a, and minus 1 times 2 is minus 2. Okay? Minus a minus 2. I'll do this. Oh boy, whenever I do these things, I'm always so afraid of making a mistake where I minus a minus. Or rather, well, I'm supposed to minus a minus. That's a plus. But I can do this. What? Wait a second. That cancels. That cancels. Are you kidding me? So this is equal to just a plus 1 times a squared. Really? Did I make a mistake, or is this good? That looks kind of pretty. So, okay, seems to be legit. So if I do this, then if I actually multiplied this out, I would get a cubed plus a squared. All right, thankfully we have over 200 people who are watching who are pretty good at math. So please tell me if I made a mistake. Because right now I'm looking at this and I'm saying, wow, how did I get that lucky? Is it really supposed to be this pretty? Is there a better way to explain why this thing might happen? I'm a little curious. It seems like there's some reason why a lot of this stuff canceled out at the end. So I guess I'm a little curious. Why is it so nice that a minus 1 times a plus 2 minus the a minus 2 happens to be a squared? I don't see a great reason, to be honest, just looking at this right now. So I guess what I'll say is probably the person who made the question and made a neat observation that you can do this and subtract that and it all cancels nicely. I like that. That's cute. And I was trying to think, would I have any other way to try to do this in an easier way? And I don't really see that there's a nicer way to do this, because of course you'd factor out the common factor, and then after that you expand and you try to subtract. Neat. Okay, I like it. I learned something today. Thanks for sharing the question. Anonymous asks, how do you tell a fish has gone bad? Because it smells fishy. Next question. Oh, neat. So Mohammed Al-Majad has asked a question about GCDs. Mohammed Al-Majad asks, if GCD, the greatest common divisor of A and B, is equal to 1, does this determine GCD let's write a better C, A, comma, 2B. What do you guys think? If somebody told you that the greatest common divisor of two whole numbers is 1, meaning they have no common factor, can you tell anything about the GCD of A and 2B? That was a car, by the way. Nice car. People like noisy cars around here. Well, it kind of does, says plausible thing. I mean, it's plausible that you might know something about this, right? In the sense that the GCD of A and 2B, there aren't that many choices, okay? There aren't that many choices. The answer is that the GCD of A and 2B, it can only possibly have picked up a 2, right? Think of it this way. You have A and B, which are made of different primes, okay? A is made of these primes over here. B is made of those primes over there. So they're just not the same kind of primes. If I have A and 2B, 2B gets another thing multiplied by it, also a 2. Okay, so let's think of it this way. So A uses the green primes. Obviously, some primes are green. And B uses the yellow primes. Now, if I look at A over here, it still only uses the green primes. But the 2B now uses the yellow primes and 2. I'm just going to write 2 in pink because we don't know what 2 is. Is 2 a yellow prime? If 2 is a yellow prime, then there's still no GCD other than 1, right? If 2 is one of these primes that was part of the B, that's not going to help you have a greatest common divisor with this thing made of only the green primes. So it's possible that it's 1. Or, if 2 happens to be one of the green primes, then suddenly you have a common factor. The common factor is the 2 itself, because the yellow stuff doesn't help you at all. And if the 2 happens to be neither a green prime nor a yellow prime, it's just like some other pink prime, then it's not going to give you any common factors with the green primes. So that shows that the answer is either 1 or 2. It's 2 only if 2 happens to be one of the prime factors of A. So I can actually write that down. It's 2 precisely when 2 is one of the factors of A. Okay, that was kind of a neat question. We could just talk about this as thinking of greatest common divisor as, building numbers up by multiplying together some primes. More questions. Ooh, Elemental has asked how to make 147 using 4 fours. Let's try this. So, we get 4 fours. That's a weird 4. How to make 147? Let's see. Anyone have any ideas? How can you make 147? So now you might wonder, what's the big deal about 147? What is the big deal of 147? Now, I actually have been looking at the number 147 for a while. I'll tell you the reason I've been looking at 147 for a while has to do with Novid, which is the app that I've been working with a team to build to stop the spread of COVID-19. And we're doing a lot of things with sound, with audio. And 147 is a number that comes up. I'll tell you where it comes up from. In what we do, we actually often have to record sound from the microphone. And when you record sound from the microphone, you record it at what's called a sampling rate of 44100. So 44100 happens to mean that 44,100 times per second, your microphone is measuring what the sound level is. And that makes this little wiggly wave that you can then play on your speaker. But why did I see 147 so much? It's because if you divide this by 3, 100, not 3, divided by 3, you get, what is it? 1, 4, 7. So this is kind of neat. It's 147. So I happen to know that 441 divided by 3 is 147. which is completely useless for the purpose of this problem. But I just thought it was neat. You have a number 147. I've been staring at 147 all the time because in part of what we are doing, we actually are doing something about 1/300th of a second. We're using 1/300th of a second on purpose because when you divide this, you get this nice number, 147. And right, 441 is also special. 441 is 21 squared. Okay, so we don't know how to do this yet. Let's collect some stuff. 441 is also 21 squared. That's equal to 3 squared times 7 squared. And that's how 147 has a nice prime factorization. That means that 147 is going to be equal to 3 times 7 squared. Is that useful? I don't know. Not really yet. How are we going to do anything with this? So what is 3 times 47? Oh, it's 3 times 7 squared. That's 3 times 49. But how could you do this with 4 fours? There's a reason I did this. The reason I wrote out the 49 is because I'm not sure if you're trying to use factorials or something, but 4 factorial is 24. 24 times 2 is 48. But that's still not possible. I'm not getting anywhere with that. Oh, but square root of 4 is 2. Could that be useful? I'm basically seeing that I can make 48, right? The way I could make 48 so far is 48 happens to be square root of 4 times 4 factorial. But that's not very useful. Unfortunately, I still have a long way to go because that's only 48 and I've got 3 times 49. Not nice. I see Joshua Wu has done this with a whole lot of 4s. That seems like maybe too many. So maybe that doesn't work. Gee, what could I do? Is it useful to multiply things? Not really. Is it useful to subtract things? Also not really. We can do interesting stuff with square roots. Interesting. So if I'm looking at this, I'm like, well, it's also 21 times 7. Is that useful? No. That's not useful either. So what do we have here? Oh, I see. So somebody has given me a hint, which is that somehow this is a weird question. Somebody has given me a hint that this is a weird question, which is that somehow you can even like use rounding to try to solve this problem. So we're allowed to use all kinds of weird symbols. That's the hint that we got here. Let me roll this thing so I can see. Okay, so a hint that we got was that it's actually possible to use some rounding. And both 3 and 7 are 1 less than a multiple of 4. We can use 4 over 4. That sounds pretty good. 4 to the power of 4. Wow, did Harry Liu get it? He has something interesting. 4 to the 4th over 2 plus 4 factorial. Really? 4 to the 4th over 2 plus 4 factorial? Are you sure? What's 4 to the 4th? 256. Oh, this is kind of neat. So this is equal to 256 divided by 2 plus 24. 256 over 2 is 128 plus 24. That's equal to 152. Not quite, so that doesn't quite work. Oh, did I also add wrong? It's entirely possible that I added wrong too. So if I have this 128, oh, okay, I think this is okay. 5 off, you're saying. All right, so now maybe it's time to do some weird cheating. All right, so somebody told me you can use these kinds of, somebody told me you can use like round down. All right, so now if we want to use round down, I think we might be able to do something that's a little bit weird. Okay, watch this. Suppose I just write down a 4. Does this work? I'm trying to think if I can cheat enough with this. Does this work? Yeah, this is pretty powerful. Okay, watch how many weird numbers I can make. I'll take the 4. I'll take the 4 factorial. Now that's 24. We know that's 24. But look what else I can do. 4 factorial. I can take a square root. Oh, that's weird. Why would anyone want to do that? I'll tell you why I want to do that. Ceiling. I rounded up. Look at that. I made a 5 and all I used was 1 4. Now you can see that I can do all kinds of weird stuff. I can then take ceiling, square root, 4 factorial. Factorial! 120. Now let's go and take we can take floors and ceilings if we feel like it. Oh, sorry, we square root again. So square root, ceiling, square root 4 factorial, close. What just happened? Factorial. I could round up. If I round up, I get 11. If I round down, I get 10. Oh my goodness, this is so cheating. So if I round down, on the other hand, if I'm lazy to write it, I'll call it same, I get 10. If you can see the power of this is I could actually probably make just about any number in the world that I wanted to. Because all I would do is I would keep taking factorial square root, factorial square root, factorial square root, more square roots, more factorials, square roots, factorials, round up, round down. You understand? I only need 1 4. I bet you can actually make 147 with just 1 4. That's my guess. Okay, so you see what's going on. It's like somehow you can actually just go and make whatever numbers you want, because you would just keep taking these square roots, you keep taking the factorials, you'd square root more times, and you just don't have anything else going on. Okay, so I'm pretty sure you can do it with just 1 4. But I don't think that's what you meant. So now I'm a little bit curious. Who asked me this question? Can you tell us what the actual answer is? If you happen to ask the question, please type it into the chat, because I'm a little bit curious if you meant for us to do something like this, which is so cheating. You're saying so do it. Okay, you want me to actually do it now. All right, if you want me to actually do it, we have so much power now that we can probably get lots and lots of things to work out. You see, let me first okay, so now that we know we can do this, which is just like ridiculously powerful, okay? Now that we know that we can do this, let's go and see. First, I just want to get somewhat close to 147, using as few 4s as possible. Or maybe using 3 of the 4s. So we did get 4 to the power 4 over the square root of 4. That was 128. That was not bad, right? And using 3 of the 4s, I can get to 128. Now I do need to get to 147. How much is left? 147 minus 128 is, really? 19. So I need 19. Can I make 19 using just 1 4? I don't know, everyone. Give me some help. So I would prefer if I got with my 3 4s even closer. Did I have anything closer over here? 48 I could get. No, that's not right. I'm trying to see what's the closest I could get with just... here's an idea. I want to get even closer to 147, all right? An idea to get closer to 147, I could do 12 squared. Would that work? Can I get to 12 squared? 4 factorial is 24. Divided by the square root of 4 is 12, all right? So I got to 12. Now, I take it to the power of the square root of 4. Look what I got. I just got to 144, I think. Right? So I took 4 factorial over the square root of 4. That happens to be 12 to the power 2, 144. Yeah? So now I need to get 147. How do I get 3 more? I see it here. I have a 10. If I have a 10, I can just do this guy and just do something really ridiculous with this guy. I can take the square root of it and round down. So here's my answer. All right? Everyone buckle up for this. So we're going to go and make 3 from this thing. And to make 3 from this thing, I need to round down the square root of... Now I need to write the 10 there. All right? So the 10 is going to go into there. What's the 10? I guess I have to go and figure out what this was. That thing. We'll use a different color. I wrote same. So 10 happens to be with the floor function of square root of ceiling function of square root of 4 factorial closed ceiling function factorial. This is 3. Okay, so now we've got 3. And with the 3, I'll add 4 factorial over square root of 4 to the power square root of 4. And that should work. I think this thing should actually be 147. But hopefully what you've seen from this is that it's extremely powerful to be able to just take all of these random square roots, factorials, round up, round down. Apparently TempID says that's my type of expression. All right. By the way, one moment please. I heard someone just came to our door, and that's because our office air conditioner broke down. Let me quickly double check what's going on. We might need to temporarily pause the stream, so we'll see what happens. One moment please. Okay? One moment please. temporarily pause the video. Please come in. Please come in. All right. I'm actually doing a live stream class out to the entire world right now. But what I'm going to do is I'm temporarily going to shut off the video. One moment, please, guys. We're going to temporarily stop this video. I'll be right back. Come in, please. It's right here. Oh, it's there. You go. Okay, that's fine. Do you want to go into the kitchen?
Did you have a ladder?
We have a ladder. The ladder is back here. It's in the closet.
In that closet. Okay, so
Yep.
I'm gonna check the filters
Right.
first.
And if you need to pass through here, just let me know, and I'll temporarily shut the video off while you get through.
Okay.
Yep. Great. Thank you. Hey, everybody. Hello, everybody. I'm right back. Okay. So as you heard, what we're trying to do is we're trying to fix the air conditioner. Life is all about problem solving. And what actually happened was that today, in the middle of the afternoon, in a very, very hot day, we actually had the air conditioner shut off. So fortunately, the person who manages this office was able to have somebody come over to try to fix it. In any case, he's now going to try to fix the filter. Meanwhile, let's keep talking. All right, next question. So now we just saw some cheating. This is pretty interesting. Did anyone actually put how to do this? Right. Okay, sounds good. Let's see, more questions. Alan Liu, the answer is yes. He does have a mask. What I'm doing right here, though, because I'm in this live stream studio, is I don't actually have a mask on right now. Oh, interesting. So somebody has actually put down the solution. And the solution did involve int, which is a rounding down. And it also involved factorials and square roots. So this wasn't too far off. Okay, more questions. Wow, looks like somebody has asked me some questions about the math homework. Somebody wants me to do their math homework. Let's do this person's math homework. Let's have some fun. All right. I won't name who this person is. This person wants us to help them do their math homework. 24v squared plus 10v minus 6. Factor it. Clearly, the best way to get your math homework done is just to show up on this live stream and ask it as a question. All right. So now how do we do this thing? Some people seem to like this or seem to think it's reasonably easy. By the way, I wanted to put this here because maybe we can see some nifty way to do this problem. So the first thing is we want to factor out a common factor, okay? So if we factor out a common factor, what could we do? Somebody said use the Po-Shen Loh method. I don't think that'll be as nice here because I can't get a 1 either there or over there. But I would take out a 2. And this is 12v squared plus 5v minus 3. All right? That's a weird parentheses, minus 3. So if I've got this, now what do? Now you have to go and start guessing. Oh, guessing. Why would anyone want to guess? I guess we're used to doing these kinds of guessing problems when you're using school. You know what? I'm too lazy. I'm not going to guess. I'm going to try to do it my own way. All right? So if I want to do it my own way, I'm going to go and now, let's see, what's the best way to do this? I want to divide out another 3, okay? I mean, it doesn't seem too hard. You're right. It's just like, do I really want to guess, though? Let's just go and divide. Let's divide out another 3. Okay, if I divide out another 3, that is equal to 6 times 4v squared plus 5 over 3v minus 1. Okay, so now if I'm trying to do this, here's what I'll do. I'm going to say that, yes, I've got fractions, but we're going to deal with the fractions later. I'm going to write this as 6 times. There will be something v plus 1 times something v minus 1. Is that okay? And the reason I wrote these two things out is because if I have any, I'll be able to find 2 numbers. And after I find these 2 numbers, I just need to find 2 numbers that multiply to 4 and that have a certain nice relationship to that number over there. I think that's what I want, right? This is what I want. No, I have an even better way. My better way, is that a better way? Thinking to myself, yeah, I want another way. I want to actually not do it this way. I want to factor out a minus 6. It'll be even better if I take out minus 6, okay? So let's take out minus 6. And what I'm trying to do here is I'm just trying to have fun with this problem. This is not what you should write as you turn in your math homework because you're watching a bunch of people just mess around having some fun with this problem. Minus 4v squared minus 5 over 3v plus 1. I want this now. So I'll say it's minus 6 times something v plus 1 times something v plus 1. Okay, now watch. We're going to start to have some fun. So I just need to go and find 2 numbers that multiply to negative 4 and that add to minus 5/3. Find two numbers that add to minus 5/3 and that multiply to minus 4. And I'm not saying this is the most efficient, but we're just going to have some fun. I just decided I don't feel like guessing, okay? So I don't feel like guessing. How do I find two numbers that add to minus 5/3 like this? What's the average of the two numbers if they add to minus 5/3? Then their average is minus 5/6. So I have minus 5/6 minus an unknown and minus 5/6 plus an unknown. All right? So now I'm just going to say, I wonder if I could figure out an unknown that will work. I just want to know, is there a u so that when I multiply these two, I get minus 4? Could I do that? If I multiply those two, it's a difference of squares. 25/36 minus u squared. Actually, you can figure out what u is from here. Let's just put it in. So the u squared goes to this side. The other side is 36. And then there's a 25 plus. Does anyone know what is 36 plus 36 times 4? What's 36 times 4? Sounds like 144 to me. And it's a 5, 12, 13. It's like the right triangle. 5 squared plus 12 squared is 13 squared. So that's equal to 169, which is 13 squared, over 6 squared. Aha! So that's a choice for you. So what I'll use for you is 13/6. That will work. Minus 13/6 also works. But if I go up here, now I've got it. So I got minus 5/6 minus 13/6 and minus 5/6 plus 13/6. These are the two numbers. And this happens to be minus 18/6 is minus 3. This happens to be 8/6, which is 4/3. And now I'll put the numbers here. 4/3. And I have also minus 3. And now if I want to just multiply it together, I can throw my minus 6 in. And I'll throw the minus 6 in by throwing the 6 into the first one. If I throw the 6 into the first one, I get 8v plus 6. And if I throw the minus into the second one, 3v minus 1. Is that true? Does it work? Let's double check. 8v times 3v, 24v squared. 8v, so it's minus 8v plus 18v is 10v. And minus 6 times minus 1, bam, it worked. Okay, so this worked. Is this the most efficient way to do it? No. But is it a fun way to do it? Yes. And then to be honest, actually, if you had to do a really crazy problem, if the numbers were really, really like weird numbers that you couldn't guess how to multiply, put them back together, actually this would in fact be more efficient. Because what I've just done is an algorithm. This is actually a general thing that works all the time. I just went and pulled out all of the factors I needed to until I knew the structure of the factorization. And then all I had to do is to go and find the two numbers that had the right sum and the right product. And at this point, when most people guess and check by splitting apart the product, you don't. You just split apart the sum instead. You cut it into half of the sum minus something and half of the sum plus something. And then you just simply solve for what is the something. I've actually just done completing the square. That's what this really is. On the other hand, it's a fun way of handing in something for your homework. And I'm pretty sure that whoever asked this, if you were legitimately asking for homework help, I'm not really sure this is how your teacher did it. On the other hand, this thing shows that we are able to go and think about normal homework problems, even with a different way. More questions. Ooh, there was a question. Kaden Xia asked, wait, how do you find the average of minus 5/3 and minus 4? Okay, that means I explained it too fast. I didn't try to find the average of these two numbers. I said, look, when I had these two blanks, my goal was to go and find two numbers to put in the blanks so that if I multiplied the two numbers together, that gave me my minus 4. And so that when I added the two numbers together, that gave me my minus 5/3. So I'm looking for two numbers with both of these things. Add to minus 5/3 and multiply to minus 4. And the trick was, start from the add to minus 5/3. If I want to have two numbers that add to minus 5/3, then I should look for two numbers whose average is half of their sum. Of course, because if I'm looking for a certain sum, then the average should be halfway in between. right? So if I want two numbers that add up to 8, their average is 4. And so I'm looking for two numbers which add to minus 5/3, so their average is minus 5/6. That's how I had these two numbers I'm looking for. And then I just go and see, what could I use for the u? And I figure it out. More questions. You guys are funny. Preston Madsen, I need help on my homework. We're going to help this person with their homework. Everyone ready? What is the Collatz conjecture? So now that was unfortunately the problem that we did a few live streams ago of start with any number. If it's even, divide it by 2. If it's odd, multiply it by 3 and add 1. Show that you eventually get to 1. Here's what I'm going to say. Your teacher is one tough teacher. No human being knows how to solve that problem. More questions. Jacqueline So asked, do you have a mask? Yes, I do. I just don't usually put it on while I'm doing the live stream itself. Is it actually over here right now? No, it's over there on my desk. Okay. More questions. What else do we have here? Can I see your mask? I'll bring it next time, okay? I'll bring it over here next time. What else do we have? Michael Dong, how to spend money wisely? That's a good question. I'm going to give you an answer that you were probably not expecting, okay? There's, of course, the interesting thing called whenever you have money, you try to use it wisely. You don't try to waste your money. Don't buy things that are too expensive. I'll give you a real-life tip. The best time to buy stuff is the day after American Thanksgiving, or in that week right after American Thanksgiving. So if you can afford to wait, if you not afford to wait, if you don't mind waiting on buying stuff, what I often do is I just wait on buying all my stuff until like the day after Thanksgiving and then just buy whatever stuff I needed for the year. That's one way. There's another important thing to know. If you ever want to buy candy, you know what's the best day to buy candy? This is an important thing to know. What's the best day? What's the best deal on candy in the United States of America? When's the best time to buy it? Yes, that's correct. Joe's Gaming Channel, the best day to buy candy is the day after Halloween. And similarly, if you want to have a Christmas tree, do you know what's the best day to buy a Christmas tree in the United States of America? Well, clearly, the best day to buy the Christmas tree is like a week after Christmas, when there are all these Christmas trees just lying on the roadside. So I'm just giving some of these things. Unfortunately, buying a Christmas tree the day after Christmas is not very useful if you wanted to use the Christmas tree to celebrate Christmas. But if you ever want a plastic Christmas tree, those might be going on sale at that time. But I'm just giving you these examples. It's like the world is not always like same prices for everything. And if you're aware of how much things cost, using your math, you can actually figure out how to let your dollars stretch farther. Now I'm going to give you another kind of answer. There's something else to know about how to spend money wisely. It's actually also possible to spend money and then earn money by spending it. That's called investing money. So when you buy a stock, you actually spend money in the sense that you spent some money and you bought some piece of paper that gives you the right to have some stock. But if you then invest in the right way, then it ends up being worth even more. So the second major piece of advice on how to spend money wisely is to spend it, but to buy low and sell high. Okay, I maybe that's enough jokes, but I'll say I actually myself worked on Wall Street for 2 summers. And indeed, that's actually what we often do. When you're working in the finance world, you're often thinking about how do you use your mathematics skills to decide what to buy at the right time. More questions. Okay. Oh, winter rain. What's the sum of a triangular number formula? I'm curious. Maybe that would be the last math question that we do today. So we want to talk about the sum of the triangular number formula. So the triangular numbers, what are they? The triangular numbers are the numbers of dots that you can get if you draw triangles. So the next triangular number has a lot of dots in the shape of a triangle. And so maybe we're a little bit curious. What happens if you go and add up all of these triangular numbers? Well, I could try adding them. 1 is 1, 3 is 3, but 1 plus 3 is 4. So if I add up these, I get 4. Now if I add up 4 and 6, I get 10. And if I add up 10 and 10, I get 20. So the formula looks like 4, 10, 20. But temp ID says something to do with Pascal's triangle. Did I hear Pascal's triangle? Let's try to draw Pascal's triangle. 1, 1, 1, 1, 2, 1. What we always do is we add up the two numbers which are above, and we put the sum underneath. 3, 3, 1, 1, 4. Now 3 plus 3 is 6. 3 plus 1 is 4. 1, 1, 5, 10, 10, 5, 1. I promise you the next row will be worth it. 1, 6, 15, 20, 15, 6, 1. Does anyone see a pattern? There's an interesting pattern going on here. Look, 1, 3, 6, 10. Where do those come from? There's a 1, 3, 6, 10 over here. These are the triangular numbers. But what about the 4, 10, 20? Actually, there's also, it goes 1, 4, 10, 20. We forgot the sum of just this one by itself. It's 1. So 1, 4, 10, 20. Oh my gosh, that's here. So what we just found out is that, in fact, if you add up a bunch of these numbers, you actually get the next number, which is down here. This is called the hockey stick identity, because it looks like a hockey stick. Don't know if anyone here is from Canada. But anyway, there's a way where you add up all of these binomial coefficients, all of these chooses. That's what these really are. And the answer is the next choose that's right down here. And the reason for this, the reason why this works, you can actually see is because that's how Pascal's triangle works, right? If 1 plus 3 plus 6 was here, and if 1 plus 3 plus 6, let me do it like this, okay? Let's suppose that we already knew that 1 plus 3 plus 6 was equal to 10. Suppose I knew that. That's why I'm circling both of them in blue. Now, what happens if I do 1 plus 3 plus 6 plus the next 10? If I do 1 plus 3 plus 6 plus the green 10, then the answer is the blue 10 plus the green 10. Of course. Of course it's the blue 10 plus the green 10, because the 1 plus 3 plus 6 was the blue 10 in the first place. And if you add the green 10, look what you get. You get the thing right under. The 10 plus 10 is 20. This is actually why it just keeps going along on this diagonal, because of something called mathematical induction. If I added up all of these so far and I got this one, if I then try to add this one on top, then the sum is going to be this one. And it just keeps going. So if you actually wanted a formula, the formula is just whatever the formula is for these numbers. What are those numbers? Well, if I want to look at those numbers carefully, let's select them all. Those numbers are things choose 4 things, I think. No, choose 3 things. 3 choose 3 is the number of ways to choose 3 things from 3 things. And that's equal to 1. Oops. Next, 4 choose 3 is the number of ways to choose 1 thing from 4 things. That's 4. 5 choose 3 is the number of ways to choose 3 things from 5 things. And you can actually work out that it's 10. 6 choose 3 is the number of ways to choose 3 things from 6 things, and it's 20. These are the numbers in the Pascal's triangle. And in general, if I wanted to know what was n choose 3, that's equal to n ways to choose the first one, n minus 1 ways to choose the second one, and then n minus 2 ways to choose the third one, divided by the number of ways that I can change my order of choosing, which is 3 times 2 times 1, 3 factorial. And so what that shows you is that this is a formula for the sum of the triangular numbers. And so the answer is yes, there's actually a real answer to this question that you asked. If you want to add up the triangular numbers themselves were just things choose 2. And so what this is it's choosing 3. Okay, more questions. I saw a question come in. Can you use math to make a good meal? The answer is, if you don't use math, you typically make a very bad meal. And the reason is because you need to use proportions. Whenever you go and mix any kind of ingredients, you usually have to go and make sure everything's proportional. You don't go like, well, you're always supposed to put a stick of butter in cookies, even if you make just 1 cookie. That was a doorbell. That was also a sound effect. But no, what I mean is like if I say every time I make cookies, I always use an entire stick of butter. If you try to use an entire stick of butter and you make one cookie, this is a very bad idea. That would be a very buttery cookie. It would probably be almost impossible to eat. Basically, the cookie will just be all butter. But similarly, if you go and take like a giant batch of flour and you still put one stick of butter in, you'll have a pretty lousy cookie also. So the way to make good meals is to use math. Okay, what else do we have? So we have about 2 more minutes. Usually in the last 2 minutes, I just go and choose some interesting question that's more general. I see somebody has said, but butter is yummy. You're right, butter is one of the secret parts of making a good cookie, or margarine, or whatever your favorite is. Let's see. What's a good question to end with? Amy Fan asks, what is my IQ? I don't know what is your IQ, but I'll tell you that whatever your IQ is, it doesn't really matter. A lot of people are always asking about, like IQs and what is my thought on IQ, and you're curious what is mine. I don't even know what is mine. My general opinion about IQs is IQs come from a test. Every single test in the world can be prepared for. And so if you just prepared for the IQ test, you'd probably have a very high IQ, which would not really mean much. So I'm not a big fan of any of those kinds of things. My way of just thinking about, can a person think? If I want to know how good a person is at figuring stuff out, honestly, I think that the best thing to look at are just how do they handle very complicated questions that they haven't seen before. And, everyone's at a different level of math. For some people, if you look at these math contest problems, those will be the level that's challenging them. Other people, it might not be that they're used to math contest problems. Maybe the school problems are also interesting and challenging. But I ultimately look at how does someone handle the situation where they don't know how to do the problem. This is also how I do interviews when I'm hiring people. I'll ask them how to do something, and if they already seem to know how to do it, I'm not really interested. I just want to know how they'll adapt to the new situation. So IQ is not as important in my opinion. What's much more important is for you to be constantly challenging yourself against hard things that are unfamiliar. Sort of like this live stream, like what you see going on here, where we're all just kind of thinking, and somehow, after all the creativity of the crowd, we managed to make 147 with 4 4s. Unfortunately today, we have run into 5 o'clock. So unfortunately that means that today's Ask Math Anything will have to come to an end. But we'll be back tomorrow. And hopefully, tomorrow, we'll also have air conditioning in this office. I hope that everyone else here is able to stay safe, I was going to say stay warm, but that's the wrong part of the year to say such things. But stay cool, and I'll see you all tomorrow.